Okay, we're going to start off with a little setup here, which I don't normally do. I have up on the board the equations. Well, I have a capacitor and an RC circuit, and an inductor, an RL circuit. Okay, and we're going to see how they're similar and how they're different, and so we can try to develop some of the equations here for the inductor. Okay. Now, what we're going to do, this just starts off right here with the Kirchhoffian loop. It just sounds cool, Kirchhoffian. Okay, I go across this battery, I gain potential E. I go across the resistor, voltage across the resistor is IR. I go across the capacitor, it's Q over C. Okay, and I'm back at the beginning here, so that all has to equal 0. So I rearrange, okay, I kick E to the other side, multiply everything by -1 to make it positive. IR plus Q over C equals E. Okay. Now I'm going to divide both sides I'm going to divide everything by R. So I is, well, it's dQ dt. This becomes 1 over RC times Q, and this is E over R. Now, from that, we were able to see that my charge on the capacitor here was equal to CE, the EMF, times 1 minus e to the negative t over RC. Okay? Right here, this is our time constant, RC. Okay? So I have 1 over RC here, and I have 1 over RC here. Okay? Time constant, tau, is equal to 1 over RC. Just make sure that's not, I think it's actually time constant, excuse me. I don't want to say that wrong, I think it's actually RC. Yeah. Okay, time constant's not 1 over RC, for crying out loud. I don't know why I wrote that. Tau, the time constant, is equal to RC. So now, when you've gone through one time constant, okay, the charge on your capacitor is equal to 0.63. CE is going to be what it is after a very long period of time. So tau is equal to RC. I'm going to leave that in blue to show my shame because I wrote 1 over RC. But anyway, okay, something to note right here, just a little side note. How did we come up with this CE? Okay, well, I have 1 over RC, so this is right here. This is really key. This RC here is really key. Okay, let's just take a look at that. Now, if I take that RC and I multiply by E over R, why would we do that? Well, you'll learn at some later time. Probably not with me. Okay? Well, I do that, and we're just trying to find a pattern here. Like, one of the things that they talked about on Cosmos was that we're great pattern finders. And it's not so much that this is a proof of why this works. We just want to find the pattern to see if it does work. Okay? So that RC here, multiplied by the E over R here, I'm left with CE. Hey, look at that, CE right there. Okay. Keep all that in mind as we go through to the next part. Okay, with the inductor. Now the inductor here, this is equal to, okay, the voltage across the battery is E. Switch is closed, so now I've got my minus IR. And last video we watched was L di dt. That all equals 0. So now, again, I'm going to rearrange. Okay, I'm going to put di dt all the way over to the left. Okay, so I'm going to have L di dt minus I. I'm going to go R times I, and I want to keep that I by itself here. And I'm going to kick E over to the other side and multiply everything by negative. Now I'm going to divide both sides by L. So di dt, we're not going to do anything fancy with that. We're not going to call it anything. It's just the rate at which the current changes. Minus R over L times I is equal to E over L. Now take a look at this. Okay. Here I had 1 over RC, I flipped it over, I multiplied it, made it RC. And I multiplied it by this. Let's see what happens when I do that now. let me flip that over. I get L over R times E over L. L's drop away. This leaves me with E over R. Now, I wanted CE before because that was voltage. Okay, that was the charge. Okay, CE is the charge, the maximum charge. Take a look at this. This is plus. Take a look at this, okay? Now, this right here, R over L, okay? 1 over RC went right in here. So if I look at the current as a function of time, and this is not charging up. You don't get an inductor to charge up, okay? Inductor will build up a magnetic field. The current as a function of time will look very similar to this, except for instead of CE, we have E over R, which makes sense because E over R is current. Okay, 1 minus E to the negative. Now, 1 over RC here, 1 over RC here. I don't have 1 over something here, I have R over L. This will be R over L times T. Well now, tau, your time constant, will equal L over R. Okay. Your current at 1 tau will equal 0.63 E over R. Okay. Very similar format, okay, except for instead of 1 over RC, you have R over L. Again, it still depends on the resistor. The resistor helps restrict the amount of total current. Now, the other thing to notice too, okay, with a capacitor, okay, the charge on the capacitor was important, but it only was important so far as it helped us figure out the current, okay, because we could take the derivative of the charge and find the current. So you started off at E over R and you dropped off. Now, here's the thing. Looking back at this, the charge, the graph for the charge, remember, you started off at 0 and you went up to some value. Here, it's the exact form of the equation. It's the exact same form. Okay? The maximum value for this would be CE. So if I put up a graph of charge versus time, let me go ahead and do that. You guys know that this is a capacitor now. The equation for charge for a capacitor, and this graph will still be important, so we don't erase it. This will equal CE, Q down here, and this is versus time. And it looked like this, and we had something that looked like that. Okay. Now, here's the thing. This and this, okay, charge for a capacitor, current for an inductor, have very similar equations. Okay, that is my current through an inductor. Now, notice, okay, now let's compare the current from a capacitor to the current through an inductor. The current from a capacitor starts off at E over R, drops off to 0. It starts as a break and ends, it starts off as a wire, ends as a break. An inductor is just the opposite. Okay? It starts off at 0, goes up to E over R. It starts off as a break, it ends as a wire. Okay? Now, there's a bunch of other things that you guys should be focused on. I am going to assign you guys problems 44 and 45 because I'm sure one of the questions in your mind is what happens to an inductor in series and in parallel? And that will be one of your questions. There will be a bunch of problems. Unlike other chapters, this one actually has like 108 problems. In the last one, you had 93, so there's 15 more problems that are possible to do. You're obviously not going to do all that, even with all of your spare time that you have over spring break, because, I mean, who wants to do fun things over spring break? All right. Now, energy stored in a magnetic field. Okay. Let's see what's Li dt. So now, if we look over, I'll do that real quickly here. Energy stored in an inductor. Okay, we talked about with capacitors previously. So now, if you look at that, we had E is equal to IR plus L di dt. Well, multiply everything by I. EI is equal to I squared R plus Li di dt. This is the power from the battery. This is the heat, it's power resistor that goes off as heating. Okay. And this is the power rate of energy usage of the inductor. Okay. Now, we are going to store energy inside the magnetic field. So our L di dt, okay, is the power, okay, which will equal, but if I look at it in terms of energy, okay, du dt is equal to L di dt. Okay. So if I just want to look at amount of energy, Li di, yes, you can kind of multiply everything by dt. Really doesn't work, but for our purposes, we'll let it slide. Okay, we're going to integrate 0 to u, 0 to I. I think your book actually calls it UB, and you're not supposed to put I in there, but it is what it is. This will be UB, the energy, the magnetic field, current in the circuit. I'll call this I star for make math teachers happy. Okay, so this becomes the energy stored in that magnetic field is equal to 1/2 Li squared. I'm not going to get into the voltage or anything else like that. We do know that it's L di dt. So we really, for the voltage, we really can't get into that too much. This is similar to the Q squared over 2C for for that energy density of a magnetic field. Oh, that was for capacitor. I was saying. Sorry for trailing off. Energy density of a magnetic field. Read it. Read section 30-11 on your own. It's not very hard. It's not very long. Okay. I want you to take a look at that. Mutual induction. That's interesting. It's very interesting. Not a whole lot of that on the AP test, so I'm not going to cover it. You might want to read that though. So I'm going to take a look to see if I've seen anything. I've never seen anything on mutual induction, so I know you guys have enough to do. So we're going to look at, I'll probably give you one problem from energy stored in a magnetic field and one problem from energy density of a magnetic field. And most of this will come from RL circuits, inductors and inductance, induced electric field, well, maybe a little bit with induced electric fields. Induction and energy transfers, I will give you 2 problems from. And then you'll get a lot from Lenz's law, which that Lenz's law, section 30-4, basically combines Lenz's law and Faraday's law problems together. So you will have plenty of problems to do, and some of them will be tough. All right. I will write the problems on the board, so while you're not doing physics, enjoy spring break. In fact, while you're doing physics, you should be enjoying spring break. I will be doing physics and enjoying spring break. Well, a little bit.